Hello, everyone. Welcome back to the main session. Last session, we of course worked a bit on the basics of 3D constraints and parameters. Following up with this, now that we know how to create parts, how to parameterize them a bit, we are going to move over into assembly design. So with the background of creating the parts, we will see how we can put them together and make an assembly structure of parts. For this exercise, I will be opening up the engine assembly as seen here in the handout. Once again, this will be the chance to see and just see what I am doing in these exercises. And then in the same format, we will go back into the breakout room afterwards. So to start, I will go to the assembly design folder, starter files, and open up the engine assembly. Now we can see in the mechanical browser, this part also has quite a few constraints. These constraints is what keeps everything in place and keeps the parts connected to each other. I can scroll through them and you can see there's quite a bit of them. And you will also see that we have some external references and blocks here. For example, the cylinder block as highlighted here. I can actually choose to hide this by right-clicking on it and hiding it. Then you can see all the internal components of the engine. And all of these different parts are represented in the mechanical browser. You can see there are parts such as the crankshaft. You can see this here. This piston assembly has an expandable and compressible plus sign and minus sign here. You can see it is a sub-assembly that consists of two parts underneath it. And you can see this is the case for quite a few more of the parts. So to start with, we want to retrieve some more accurate information also on the parts that are in here. You can see them in the mechanical browser, but we can also retrieve some info on them through using a bill of materials. I will go into the Layouts tab on the bottom of my screen, and I will go to the Assembly tab on the ribbon. From here, I will see the bill of materials option, select it, and then I can see in the command line dialog at the bottom, I have some different options for this. Right now, I want to just place this default configuration. I'm going to place it on the right here. This is now a top level bill of materials, meaning that it will show things such as the cylinder block, the crankshaft, and the piston assembly. The piston assembly being the top level component or top level part in this, and the subcomponents will not be shown in the top level view because it will only show the top parts here. However, if I go back and place another bill of materials, I can go to the command line dialog at the bottom of my screen and select bottom level. Then you can see the bill of materials is a bit longer. And if I place it, you will now see that things such as the piston and the finger component here will also be found in the BOM table. So the bottom level will show all the components within the assembly, all the subcomponents as well, while the top level will only show the top level of parts. So moving on from this, I will go back into the main assembly. You can see there are two pistons and two connecting rods for each instance of the pistons on each segment of the crankshaft, except for the last one. So we will be adding on this to another one to the last segment here of the crankshaft. To do this, you can simply go to the top part of the screen on the ribbon under the Assembly tab. Here you can see the Insert Component option, or you can use the command BM Insert. In the file structure, you can see the folder assembly design, starter files, and here we are going to insert the connecting rod assembly, in fact. Now it is hovering in the model space, and I'm just going to place it here. And that way we now have this part as well in our assembly. I also want to place another part. I want to place the piston assembly. So I will repeat the step to insert the piston assembly component as well. And just click to place it. Now, of course, they are just hovering freely in the model space right now, which is why we will use constraints to place them together. Previously, we placed constraints on the part level, but we will now also use it on the assembly level. So the knowledge you have from working on the part level and making constraints and parametric parts will also be relevant knowledge for assembly contexts. So I will first start off by using the concentric constraint on the top of my screen here. Concentric meaning that we can make two parts share the same center. Since we have two cylindrical features here, I'm going to select the cylinder of the connecting rod, and I will select the shaft here on the piston assembly. It will then move into place, and they will now share the same center. I can do the same thing, but use the coincident constraint and place coincident on this face. And I will place the other coincident constraint selection on this face, meaning that now these faces will be touching. Of course, I can add a distance constraint between them to make the distance between them even, but the rest of the assembly is configured this way. So in this instance, that is not important. And now we have these two parts connected. So for example, if I try to move just the connecting rod, the piston assembly will also move along with it. We still have to attach it to the actual crankshaft as well. So that way we can use the same constraints. So the concentric constraint, I will place that on the internal face here and on the face here. And now they will share the same center. You can still see that it is not placed correctly according to where it should be on the shaft here. So we can then choose to move it into place if you wish. Or we can use a distance constraint to control the distance between, for example, this face and this face. So all I'm doing is placing a distance constraint between them. I can then see the value of it the same way we did with the thickness on the previous exercises. But now it will determine the distance between them. And I can give it a value of 20 millimeters, and it will move into position. Also, it is not in the right positioning compared to the others. You can use the rotate commands to rotate it into place, or in my case now, I will just use the parallel constraint. So I will place a parallel constraint on this face, for example, and make that parallel with the face on this connecting rod. This is because the current or the positioning of the connection of the crankshaft here, this shaft is in the same position as this shaft. So these should be identical in positioning. And therefore I will use that to make them parallel with each other. I'll also apply that to the top of it, like so. Now, we can see that it has been attached to each other. Everything is constrained. If in the mechanical browser, I now have the new constraints that I placed, the concentric and coincident constraints, as well as the dimension or the distance and the parallel constraints. So that is all well and good. We are going to add some more parts to the assembly. We can see here now that the connecting rod assembly does not actually have any bolts to keep these two parts in place. So that is what we will change next. If I select it, you can see it will be highlighted in the mechanical browser. From here, I can choose to open it, or I can also do so from the quad as well. Or you can also go through the files and find the relevant file and open it that way. But it is quite easy to do it through here. Here you can see the sub-assembly of the engine. This also then in turn has its own constraints to keep everything connected, because it does consist of the beam here for the connecting rod and the cap on top. So they are already constrained into place for us. But we will add some bolts to, of course, allow it to be a more realistic representation of what it would be in real life. BricsCAD Mechanical offers a library panel, such as the one you can see on the left here. If you do not have this open, you can, like before, right-click on the ribbon, hover over panels, and find the library option or library panel. From here, you can go through the different folders, such as standard parts, fasteners, find the bolts, and then find the type of bolt and the standard that you want to use. Of course, this is one way, but if you already know what bolt you want to use, like in this case, it is already given to us by the manual. So I will type in the standard name, which is ISO 4017. So I will just type in 4017. And here I find the exact bolt standard that I wish to use. Now I can place this in place already, but you can see it is a bit too large for our assembly. You can place it and then change the parameters of it later, because these parts are fully parametric. But you can also change the parameters as you are inserting them. So if I go to the properties panel on the right side here, you can see I have the part number value, I have a size and a length. And from here, I can go through the different definitions here, and I can change the sizing and the length of it. And according to the manual, it should be M10 times 1.5. So I will select that. And I will change the length from 80 to 40, which is now more appropriate for our assembly. Now we have to place 2 bolts, so you can do repeat this step twice if you wish, or you can go to the command line dialog where you can see the option multiple. Select the multiple option, and then that way you can insert several at once or after each other. We want to place it on this face in the center of this hole. And like previously, when we have sketched on a surface, you can lock your selection to that face by pressing the Shift button. So I can do this now also. By clicking Shift, I lock this placement onto this face. Even if I go outside of the face, it will remain in this plane. And then I can hover over the center of the hole. You can see it will highlight the center for me. If you do not have this option, you can go through the eSnap settings as shown previously. Also, while placing, you can hold down the Shift key, right-click with your mouse button, and then you can get a very quick access to the eSnap settings, and you can enable center here if you did not previously have it. And you will still remain in the placement of the bolt. So I will place it there. Staying on the same plane, I will also place it in the center of the other hole, like so. Hit cancel to see it like so. And you can see it is the perfect length for this hole as well. And the assembly should be now complete here, or at least the sub-assembly. Now that this has been done, we can then go ahead and save this sub-assembly so that we approve and save this settings or the changes to the model. If we then go back to the engine assembly, we can now see that nothing has changed just yet, but we can go back to the mechanical browser, right-click on the root node of the assembly and select the update option. This will update every single thing in the assembly, and you can see the bolts will appear. And it did so on all the other parts as well, because it is the same external reference that has been used and reused for all of these instances. So if you change their source file, then all of these references will also update. Just to show you, we can go back to the layout tab. And here we should update as well. And you can see in the top level of the assembly, the top level view of the bill of materials, nothing has changed. This is because if you go to the mechanical browser, you can see the connecting rod assembly and all its subparts. The bolts are now considered subcomponents of this assembly, meaning that in the top level view, they will not appear. However, in the bottom level view, we will see all the different parts so every single part that appears in the assembly. And here you can see the ISO 4017 and 16 of them are appearing now in this bill of materials. Following this, we also can see that the crankshaft is just hovering in thin air, basically. We, of course, want to add some more support around here and something that will allow it to rotate, which would be then a ball bearing in this case. So once again, we can go to the library panel and we can find ourselves a ball bearing. You can do this again, going through the folder system, or you can search for the value given in the handouts, which will be DBRG-30. I can select this and hover into the model space. Once again, it is quite large compared to what we need. So once again, we can go to the properties panel and change the value to 40 millimeters. Which is more appropriate for our use. So then I can also use the multiple option. I can place one ball bearing here and I can place one on the other side, for example. Then we also need to constrain these into place, like previously with the other parts. We can use the concentric constraint on this surface, this circular surface, and the internal circular surface of this, making them share the same center. Once again, for the other side as well, this circular surface and this one. Then we can either use a distance constraint or just a coincident constraint to make sure that it is placed flushly with this here. And same on the other side. You can feel free to use a distance constraint to try it out and place it in the middle here also if you wish. So then we have added these components. These components are now inserted into the main assembly, meaning that they are not subcomponents of any other subassembly. So now, in theory, these ball bearings should appear in the bottom level bill of materials as well as the top level bill of materials. So then we can see, go and check, and maybe I am proven wrong, but probably yes. So you can see here the ball bearings now appear in the top level bill of materials with a quantity of 2, and it will also appear in the bottom level with a quantity of 2 as well. So now the assembly is completed. You can then see everything is connected well with each other. And something else cool is that you can see everything engaging with each other if you rotate the crankshaft. So I will just use the manipulator and I will rotate the crankshaft. And you can see that it will retain the constraints that I have placed on the assembly. And you can see them rotating and behaving as an engine piston. that is the end of the first exercise. I'm also going to throw in an extra exercise for you. This is just because it will add a bit more of volume training in terms of placing constraints and forming components. Once again, it will use the communicator for BricsCAD, but we also have a intermediate file as well. So here you can see this file. This will be the next one. It is also fairly short and will just give you some more volume training in terms of the behavior of different parts and external references. So I will open up a new drawing, empty drawing, go ahead and choose the import option. Oops, I will go back to my folders. And I will find the assembly inverse kinematics. Here in intermediate files, you will have the step 1, which has already been imported for you. Or in the starter files, you can find the .sat file that you can import to try it out for yourself. And here you can see an industrial robot that we have imported into our files. Now, same as before, previously, you can see probably some of the geometries are faces that are split into two when they probably don't need to be. So that way we can again use the DM simplify command on the entire model to simplify the geometry. And now you can see it's joined the circular surfaces here, for example, into a complete surface. You will see that all of these parts are now just simple 3D solids. We can then also choose to move these parts, for example. I will just move these parts upwards. You can see we can separate them quite easily from each other. And this is something I want you to do just so it will be easier to visualize once you do assemble them together again. Like so. I will do the same for the parts at the top here as well. Just so we can have a clear visual of all the different parts here in the file. Now, all of these parts are just 3D solids. There is no mechanical information attached to them. So we are going to then start by identifying the different parts. We will give them some names and so on, just so that they are more easy to identify, and we will save them as components for the mechanical assembly. So first off, we can start by giving the different parts some colors. For example, I can make this a bit darker. Or you can just go through and change the different colors as you wish. It is not super important. It's just more so for the guide so that it is easy to see the different changes or the different configurations of the parts and easy to recognize them. So this one I will just make blue following the guide. You can also change the color from the quad, actually. You don't have to use the properties panel. You can basically just select the part. Through the quad, you can see here the color option. And from here, you can select a color. I will select this one as well, turn it into yellow, turn this one into another color, and this last one into red. So they are easy for you to see. So following this, we need to form them as mechanical components. So we can use the BM form command. You can see this here. You can also go to the top of the ribbon, and you can see here the form component option. I will select the base. then you will be given the option to select a local saving or an external saving. Local, meaning that the part or the mechanical component will be saved locally in this file. External, meaning that you can save it somewhere in your file system and it will be referenced externally, like in the previous file. And this being the insertion point, essentially. So I will just select this as the external part, just to show you that I can then save it, for example, to my desktop and to this folder. Save it to assembly inverse kinematics and call it base. Then I can do the same with the other parts. Select this part. I will now choose local. And I will give it a name in the mechanical or in the name for the mechanical component in the command line dialog. I will call this one platform. And continue doing these steps for each of the different parts. This one will be called shoulder, and you will see in the mechanical browser, it will have more and more components be created as you go along with this. This one should be called arm. This smaller one should be called hand. Like so. This next one can be called grip or head, actually. And the last one will be called head. Now we have a name for each of them, and we have each component as an instance here. The base is still an external reference that I can open and edit. The other ones are locally saved, so I would have to open a copy to be able to modify them and save them elsewhere. Also, if I want the base to be locally saved as well, I can go through here and switch to local. And you will see the green arrow disappears, and now this base component is no longer an external reference. And if I want to change that back, I can switch to external. I can also do that for the other parts, switch to external, but then I will also be asked to give it a location to save to. Then it is time to apply some constraints to these parts. I will go ahead and just fix the entire part here in place, the entire base, by selecting it and applying a fixed constraint. Then it will not be able to move anywhere. I can use a concentric constraint on this circular face and this circular face, making sure they share the same center. Coincident constraint between these two. Following this, applying concentric between these two circular faces and concentric constraint between these. And basically we are rebuilding the robot arm to give you some practice as to how they behave and how these constraints work. And when we are finished, we will see that the behavior of the files or the models will also be kept intact if we move certain parts of them. So like so, I will select this face and this face. Then a concentric constraint between this circular face and this circular face. And also concentric between this face and this smaller face. Sometimes it is easier to select the coincident faces before the concentric constraint. It depends a bit, but you will get to see that as you work on the exercise. Make these concentric and coincident, like so. And that way we have reassembled the entire part or the entire assembly. From here, I can try to, for example, move the top part. And you will see when I move this one part, the rest of the robot will also follow along with it now that it has been constrained into place. This was not possible previously because, of course, the parts were not constrained together when they were imported. So that is some of the added value that you can get from constraining them together. Also, you can test this on individual joints. For example, this joint here, you can see I can rotate and the robot will behave like so. Now we can also add more parts to this. In the exercise, you will be inserting another part onto the end of it, which will be a car door. I will go to the starter files, and here you can see the car door file. I will just place this here. And conveniently for the exercise, there is a hole here, so we can use this hole to place a concentric constraint between this and this part, just for some added simplicity. And then we can also place a coincident constraint between the bottom of the hole, for example, and the end here. And then again, you can move this around and you can see the model changing accordingly. Now, if you, like I mentioned, all of these files are saved locally. We can go in and change, if we want to, for example, change the length of this component here, the hand, we can do so. I will go ahead in the mechanical browser, select hand, and here we can switch this to external. So now it will ask me to save it somewhere. You can keep the same name if you wish, or you can give it a new name, for example, hand_new. And then you can see it will now have the green arrow here. From there, you now have the option to open it. So you will open the externally saved file. From here, we can then make some changes to the file. For example, we can add some material onto the end here. You can use either the extrude or the push-pull command, I think, and we can pull this backwards 400 millimeters. Now it's made to be longer. Then we can go ahead and save it once more. Go back to the file and select the hand here. We can update this, only this part if we wish, or you can use the root node to update the entire assembly, but we just changed one part. So I will update that individually. And you can see it will extend accordingly, and it will still keep intact the constraints that we placed earlier. So I can try again to move the car door, and you will see that it is still intact with the constraints, even though it changed some of the geometry. So that is the end of this exercise. This is the last exercise for today. We are a bit ahead of schedule, so we will have then approximately 30 to 40 minutes to work on this. Just take your time, and we will go back to the breakout session when everyone is ready. So with that, we can move into the breakout sessions.
Download BricsCAD today and start your free 30-day trial.